The student, in the last class, we defined the linear independence and dependence and discuss some examples. Now this class we try to discuss some properties of a linearly independent and dependency. So first we start what the first one is a singleton set containing 0 belongs to V is a linearly dependent. So that means if we have to know this, you know that in the last exercise I just said that one example I take in the form of a 0 0 and then you have a 1 0 in R2 and this in R2. So this means this one we can just say that here you can just see this is a 0 0 element is containing here. So this saying that the set containing 0 element means if set containing the 0 element in this set, that means this set is always linearly dependent. So that means this is easiest for us. If we see any set which containing the 0 element of this vector matrix vector space, then we can say that the set is clearly linearly dependent. How we prove this? This is very trivial. We can say that 0 of V can be written in the form of a 0 of V can be, this can be written as in the form of alpha into 0 of V is containing 0 of V. In vector space property, we know that there is this alpha of 0 V is equal to 0 of a V, and alpha is belongs to the R. So this means this for all alpha belongs to the R. This means there is a not a unique solution. This means alpha is any values we can take. This is always giving a 0. So for all values of a alpha, there is a, this means this equation has a infinitely many solutions. Alpha 1 0 is equal to 0, alpha 2 alpha is equal to 2, then 2 0 is equal to 0, and so on. This means 1 into 0 V is equal to 0. We can say that 2 into 0 V is equal to 0, and so on. So that means this is clearly this linear combination, and this linear combination is a non-trivial linear combination. So if this is a non-trivial linear combination, then we can say that any set containing as a set 0 element means 0 element of the vector space V is always is a linearly dependent. Okay, so now we have a second property. If we say that if V is a non-zero element and this set is a linearly independent, if we have any set of vector V is not equal to 0. So with this means we can write linearly independent linear combination of these is a 0 vector. So alpha times V is equal to, we have a 0 vector. And now you remember that means we have to prove in vector space property V is a vector, alpha V is equal to 0. This implies that we have a either alpha is equal to 0 or vector V is equal to 0. So that means if this vector we can write in this form, this means we can say that either alpha is equal to 0 or V is equal to 0, but we have to assuming that V is not equal to 0, that means V is not equal to 0 means we have a given that what is given, we have a given this vector should be a non-zero vector. If vector is non-zero vector, by this property we can then only possibility this alpha is equal to 0 means this is a trivial linear combinations. That means 0 into V is equal to, we have a always is a 0. And also this is one of the property of a vector space. We have a 0 of V is equal to 0 of a V is there. By this, or we can just say that we write this equation by using this condition where alpha V is equal to 0 means either V 0 or alpha 0, but V is not equal to 0 is a given. So alpha is equal to 0. So in this case we can say that if a set if a single set V is not equal to 0, the set is V is a linearly independent set is there. Now any set containing 0 vector is linearly dependent. So this is not a problem. We have a again this is the proof is simple. We can say that any set, suppose we have a V set can write as the form of a S is the set is the form of, we take a V1 V2 up to Vn, and we can say that any set containing the 0 vector, suppose we have a ith is equal to, we have a 0 vector. If ith position we have a 0 vector, so we can write this linear combination of this is a trivial, not a trivial linear combination, 0 into V1 plus 0 into V2 and so on, plus ith position we take a 1 into 0 plus we have a this is 0 into Vi plus 1 and so on, plus we have a 0 into Vn. This is giving you a 0 vector 0 0 0 0. This is enter. So this means this is I just write this is equal to 0 vector of this vector space. So this means this is clearly, this means we have to write if V is equal to 0, we take a alpha is any alpha, which any non-zero element quantity is there. So any set of containing is a 0 vector is always is linearly dependent. So that says we can say that this is trivially we can prove that if we have to check any set, if we have there is a two types of, if we have a single set 0 is always linearly dependent, because we have to prove that. And also if a set 0 0 comma, we have to take any set which contains for example you take a set of vectors V1 is equal to, in R3 we take a suppose 0 1 0, V2 is equal to we take a 1 0 0 and V3 I take a 0 0 0. That means this sets is always is linearly dependent. Why? Because this is the if we have a S is equal to V1 V2 V3, V1 V2 V3 are in this form, and this is linear combination is we can write 0 0 1 0 plus we can write 0 1 0 0 plus we have a 1 times 0 0 0 is equal to 0 0 0. So in this case this combination is again is a non-trivial linear combination. So if we take any set of vectors, the 0th we take a ith position is 0, where somewhere is a any position is a 0, we take a nth position is a 0. So that means we choose a one vector in this set is equal to 0 vector, and then that 0 vector is any non-zero values into 0 is given to 0. So this means this is, we can say that is clearly is a linearly independent. So we have a sorry linearly dependent. So in this any set containing a 0 vector is always is a linearly dependent. Okay, students, in the this we have to any non-zero set. So we take a element of this form. Let S be a V1 V2 be the set of non-zero vectors. Then S is a linearly dependent if and only one of the vector is a scalar multiple of the other. So we have a giving two vectors, and then we have a two portion is proving this S is a linearly dependent if and only if one of the vector is a scalar multiple of the other. We have to assuming that if we have a these two set vector S is equal to S is a linearly, assuming that S is a linearly dependent. So we have a assume that S is linearly dependent. If S is a linearly dependent means we have a linear combination of this alpha 1 V1 plus alpha 2 V2 is equal to 0 vector. At least one of alpha one of alpha i's, I running 1 to 2 1 alpha i's is not equal to 0, I is equal to 1 and 2. So this means we have to assuming there for the moment alpha 1 it should be not equal to 0. So if alpha 1 is not equal to 0 means we have to say that alpha 1 this is the element of a R. So 1 upon alpha 1 is also the element of a R. This is the element of a R. So this means this we can write alpha 1 V1 plus alpha 2 V2, we can add both side minus ka maybe adding into this form plus minus alpha 2 V2 is equal to we have a alpha 2 V2. We have to adding both side we can just take a because is this is equal to this thing. So we have to add minus alpha 1 V1 plus alpha 2 V2 is equal to, we just said that in this form we can write alpha 1 V1 is must be equal to minus ka alpha 2 V2, and alpha 1 is not equal to 0, so 1 upon alpha 1. So 1 upon alpha 1 we have alpha 1 V1 can be written as a 1 upon alpha 1 minus alpha 2 V2, and this be 1 upon alpha 1 and V1. This can be written in the form of a minus ka alpha 2 upon alpha 1, and then is equal to you have a V2, and then we have to just say that this implies that we can write this is identity 1 into V1 is equal to V1. So, V1 we write V1 can be written as a minus alpha 2 upon alpha 1 V2. This is the element of some scalar R. So, V1 can be written as a scalar multiple of a other. So, this means one way we have to prove that if we have this set S is a linearly dependent, then one of the scalar is a scalar multiple of the other. Conversely, if we say that one of the vector is a linear scalar multiple of the other, so we have to conversely. So, we just say that conversely we can write V is equal to, we have alpha times of a V2, and alpha V1 can be written as a scalar multiple of a other, and this can be written in the form of 1 into V1 plus minus alpha times of a V2 is equal to 0 vector. And because of this, if we take alpha is equal to 0 also, then 1 into V1 plus 0 into V2 again 0. So, this is again is a we have a non-trivial linear combination. So, if non-trivial linear combination means this is again, so this means this implies that this set is V1 and V2 is linearly dependent. So, this means we can say that in this case, for example, if we take a set of the vectors in the form of this 1 comma 2 and 2 comma 4, then this you can see this is equal to clearly 2 4 can be written as a 2 times of a 1 comma 2. So, this means these two vectors are linearly dependent. One more example, if we take we can take for the example in the form of a 1 comma 5, and then we have a 2 comma 10. In this case also you can see this 2 comma 10 can be written in the form of a, this is equal to 2 times of a 1 comma 5. So, this means again this set vectors is linearly dependent. Okay, so now if we increase one more vector, if we have a 3 vectors V1, V2, V3 is linearly dependent if and only if one of them is a linear combination of the other two vectors. So, just means we assuming that, suppose we have assume that this S is a linearly dependent. Assume that S is linearly dependent. Now, if S is a linearly dependent means there is this is non-trivial linear combination, at least one of the alpha is not equal to 0. Then alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 is equal to 0 vector, and if this is equal to 0 vector, at least one alpha I is not equal to 0, and we can assuming that say alpha 1 is not equal to 0. If alpha 1 is not equal to 0 means we can say that we can write this is can be written as a form of alpha 1, V1 can be written as a minus ka alpha 2 V2 and plus minus ka alpha 3 and V3, and because alpha 1 is not equal to 0, so we can 1 upon alpha 1 is the element of a R, so 1 upon alpha 1 is also the element of a R. So, in this case we can write 1 upon alpha 1 V1, and this is equal to 1 upon alpha 1 minus alpha 2 V2 plus 1 upon alpha 1 minus alpha 3 V3, and this is giving a, this can be 1 upon alpha 1, and we have a alpha 1 V1 is equal to minus alpha 2 upon alpha 1 V2 plus minus alpha 3 upon alpha 1 V3, and this is nothing but is equal to V1 can be written as a, I take a suppose is a beta 1 V1 plus beta 2 V2, where beta 1 is equal to minus alpha 2 upon alpha 1 is the element of a R, and we have a beta 2 is equal to, you have a minus alpha 3 upon alpha 1 is again is the element of a R. So, this means V1 can be written in the form of a linear combination of other two vectors. So, that means we have to just say that one of the vector is a if 3 vectors are linearly dependent, then one of the vectors can be written as a linear combination of other two vectors. So, now V1 can be written as a linear combination of these two vectors, then we can say that these 3 vectors are linearly dependent. if one v1 can be written in this form, v1 one of these three vectors. So this means we can say that if we have to prove that if we have a one of the vector can be written as a linear combination of other two vectors. So assuming that alpha one of the vector can be written as a, so we assuming that v1 now converse part, conversely we have just said that conversely we have a one of the v1 can be written as a alpha 1 v2 plus alpha 2 v2. So we have to write v1 can be written as a linear combination of a other two vectors. Now this v1 can be written as a 1 into v1 because we know that 1 into v is equal to v. So this is equal to, you have a alpha 1 v2 plus alpha 2 v3, and this way can be written in the form of a 1 into v1 plus minus ka alpha 1, and we have a v2 plus minus ka alpha 3, v3 is equal to 0 vector. And now if you have to take, assuming that alpha 1 alpha 1 and alpha 2 is equal to, we have a, if we alpha 1 alpha 2 is equal to 0, then this vector is again is a 1 into v is here. So this, in this case we can say that this three vectors is only possibility of this is linearly independent. So this is linearly dependent clearly because this vector is clearly is a non-zero. 1 into v plus, if we have a alpha 1 alpha 2 also 0, this linear combination is again is a non-trivial linear combination. So this means at least this first vector is equal to 1, v is equal to this here. So in this case we can say that these three vectors are linearly dependent. So now we have to one more, if we have to this property is saying that if we have a v1 v2 vn linear combination of this, that and that is v belongs to the in place of a 3 we have to assuming that v can be written as a linear combination of n vector. That means v can be written as a, that means v can be written as a alpha 1 v1 plus alpha 2 v2 and so on plus alpha n vn. If this can be written in this v1 v2 v can written in this form, this means v, if v written linear combination, this v is the span of a these three vectors. Then I say that v1 v2 vn is a linearly dependent. So this means if we have a vector space, linear span of a v belongs to any vector v belongs to the span of a v1 v2 vn, then v1 v2 vn is a linearly dependent. We try to prove this. So we can be written in this form. So we try to show that this is a linearly dependent. So we can write alpha times alpha 1 v1 plus alpha 2 v2 and so on plus alpha n vn is equal to 0 vector. And then we try to show that sorry, we have to write one more vector. Sorry, we have a alpha v plus alpha 1 v1 plus alpha 2 v2 and plus alpha n vn is equal to 0 vector. And because of this we have to write all these things equal to all alpha i's is equal to 0, and then we can say that this if all the alpha i's I is equal to 0, there is not a problem because this v belongs to the span of this. So this means clearly if this alpha is equal to 0, this means we cannot write this linear combination. So this means we can starting from here because this v can written in the span of this can be written 1 into v plus minus ka alpha 1 v1 plus minus ka alpha 2 v2 plus so on plus minus ka alpha n vn is equal to 0 vector. Now if this alpha 1 alpha 2 alpha n are 0 for example, then again we have to write, for example this can be 1 into v plus 0 into v1 plus 0 into v2 and so on plus 0 into vn. And then you can see this again is a 0 vector. Because of this we have to write in here, this is a take inverse from this we can write. If this is equal to, we can write in this form. So this means clearly we can say that again there is a non-zero vector is there. So this is a linear combination, is a non-trivial linear combination, and then we can say that if this is a non-trivial linear combination, so we can say that these three vectors are linearly dependent. These not vectors are linearly independent. This means this is the way we can just complete this proof of this all these things, and we have to say we have to complete this. So, I have to today's class stop here. In the next class we also discuss some other properties of vectors, linear independent and dependent, set some more important result which is be useful, and discuss some problems, and then we move to the basis of a vector space. So, I think I can stop here. Thank you very much.